Hello class, in this video I'll be doing another application of first-order partial derivatives. Let's begin. So as a reminder, derivatives measure the approximate change in a quantity, not the total quantity. And that will come in handy when we interpret the results of each of these problems. Okay, so the problem states, suppose the production function of a company is given by that function, where x represents units of labor and y represents units of capital. Find the following when 6 units of labor and 8 units of capital are used. And I want to find the marginal productivity of labor. And I'm going to highlight that in green. All right, so labor is represented with an x. And since we want the marginal productivity of labor, that is going to be measured with the partial derivative with respect to x. So I'm going to go ahead and write the productivity function down using a rational exponent. And to find the partial derivative with respect to x, remember, we're going to hold y as the constant. And this function is going to require the chain rule. So here we go. The 1/2 becomes a coefficient. Subtract 1 from the exponent. And the derivative of the function inside, which is x squared plus y squared, and the partial derivative with respect to x is just going to be 2x plus 0. So the partial derivative is the following. This 2 in the numerator divides with this 2 in the denominator. So this is going to equal 250x divided by the square root of x squared plus y squared. And now we can evaluate the partial derivative with respect to x when x is 6 and y is 8. And the square root of the quantity x squared plus y squared is going to be 10. So this equals 150. So how do we interpret that value? Well, we're talking about the marginal productivity of labor, which means we took the derivative with respect to x, which means we held y to be constant. So in this case, we're going to assume y, or assume the units of capital is fixed at 8 units. If labor increases from 6 units to 7 units, production increases by approximately 150 units. Okay, so as soon as I get this boxed up here, there we go. Again, notice I use the word approximately. We can use Decimus to find the exact increase in production. And so we're going to go into Decimus. And I already have the production function entered. And the coordinate we are focused on is 6, 8. Now, if 6 increases to 7, and 8 stays the same, it looks like our approximation is pretty darn close to the actual increase in production. We're only off by approximately 7.5 units. So that was a pretty good approximation. Okay, now on to the marginal productivity of capital. So I'm going to start again by writing the productivity function using rational exponents. And we're going to take the partial derivative with respect to y, which means we're going to hold x constant this time. So applying the chain rule, the 1/2 goes down like that as a coefficient. And we're going to subtract 1 from the exponent. And this time, since x is the constant, the partial derivative with respect to y is going to be 0. And then this is plus 2y. So this is going to equal the following. So this 2 in the numerator divides with this 2 in the denominator. And we're left with 250y divided by the square root of the quantity x squared plus y squared. Okay, so now let's evaluate this partial derivative when x is 6 and y is 8. And the denominator is going to be 10 again, and this is going to equal 200. Okay, so what does this 200 represent? How do we interpret this? Well, since we have the marginal productivity of capital, and we took the partial derivative with respect to y, we're going to hold x constant, and x is the units of labor. So we're going to assume labor is fixed at 6 units. If capital increases from 8 units to 9 units, production increases by approximately 200 units. And again, if you wanted to find the exact increase in production, you can use Decimus.